Welcome back. So, this chapter in the book is covering supervised learning and actually goes through closer to a dozen different types of supervised learning algorithms. Oh, that is my eraser. Good job. Supervised learning. There's a lot of different algorithms that can be used for supervised learning. If you're coming to this video with not having viewed the previous ones in order, you don't have to do that. But just to catch you up to speed, supervised learning is a type of machine learning where your, let's call them labels or classes, are known. So, for example, let's say you had a group of people and you had their shoe sizes, right? And you wanted to use shoe size as a metric to determine or predict someone's height, right? In supervised learning, you have both the shoe size and the height of everybody. And it's an unsupervised learning. You didn't have heights, and so you wanted to group people based off of their shoe sizes. Right. We'll cover unsupervised learning more in a different video, but for supervised learning, we also want to focus on K-nearest neighbors here. If you're coming in with very little to no understanding of KNN, I do recommend that you have some supplemental resources so that you can learn this properly. But just to give a quick crash course for people who just want to know what exactly this is, not so much how to do it or an example of it, but imagine we have a plot that looks just like this. You have an x-axis and a y-axis, right? And you want to group these people. Let's put some data points out here to represent our people. This is just a big old scatter plot of different data points. Okay, draw a couple more over here, and some more down here, and a couple over here. Okay. For K-nearest neighbors, this is an algorithm where you have a certain number of classes, right? In a previous video, we discussed briefly how you can do classification with as a binary classification or a multi-class classification. Okay, let's say we wanted to do a binary classification. If you aren't sure what those words mean, there should be another video covering that. So I recommend spending 2 minutes on that and coming back to here. But if not, if you do know what binary classification is, continue on watching. Okay, and before we get into how the actual algorithm works, I'm going to draw this divider line. And we're going to say everything in this region is a part of class 1, and everything in this region is a part of class 2. Okay? We want to use this algorithm called K-nearest neighbors to figure out these classes, because we're not told them at the beginning. We have to learn them through machine learning. Okay? The way K-nearest neighbors works, you have this letter K. Let's go back to whites. You have this letter K that represents a number. It might be 1, it might be 2, 3, could be 5, could be 7, could be 16, could be any number. That number is for you to choose. We're going to say, for this example, K is equal to 3. Okay? And let's say we're focused on this. Oops, undo. We're focused on this data point right here. Let's zoom in on it a little bit. This data point right here, we'll color it in so you know exactly which one I'm talking about. Right? And then we'll get rid of this little arrow. We want to know what class this data point belongs to. Okay? Our K value is equal to 3. And so we're going to look at the 3 nearest neighbors to this data point. And let's take this data point and just slide it out there. Okay? What are the 3 nearest neighbors to this data point? I see this one, I see this one, and I see this one. Those are the 3 closest neighbors to this data point. And what K-nearest neighbors will do is say, okay, of these 3 neighbors, what is the most common class value for those three neighbors. And again, earlier I drew a yellow and a purple class. Let's say these 3 points happen to be part of the yellow class. Okay. Well, these 3 data points, that's a yellow point, that's a yellow point, and this is a yellow point. So looking from the perspective of this data point again, well, the average neighbor is a yellow. It's a yellow class neighbor. So we would infer from there that, well, this point should probably also be yellow, right? And in a different example, we might say, well, this one was actually a purple class, and this one was a purple class, and this one up top was still a yellow class. Well, now the average neighbor is purple. Purple, purple. So, of the 3 nearest neighbors, most of them are purple. So then this one will be classified as a purple data point. Okay? Again, you can change the number of K. You can change it to 5, and then you'd be looking at the nearest 5 neighbors. You could reduce it to change it down to 2 or 1. That's just a hyperparameter of your model that you would choose in order to make the best model that you can based off of your data. Okay? So that's a quick introduction or refresher to K-nearest neighbors, and a couple notes I want to touch on regarding that. Okay, the first thing is this little graph over here showing that model complexity rises as the number of neighbors decreases. Okay, in general, let's say down here you have 1 neighbor, and over here you have 10 neighbors. Okay, and the way you just want to think about this, and won't spend too much time on it, is that, well, let's say for that graphic that I drew earlier, that you only wanted to compare off of the nearest neighbor, the nearest 1 neighbor. Okay, well, you're not giving that data point very many options for it to choose what class it should be. You're only giving it 1 neighbor, right? Let's say you lived in a neighborhood of 100 different people, right? And someone had to figure out what was your favorite flavor of ice cream. Could be chocolate, could be vanilla, could be strawberry, right? That person who wants to figure out your favorite flavor of ice cream gets to only ask 1 neighbor, your next door neighbor, what is their favorite flavor of ice cream? They might say strawberry, right? Then this scientist has to figure out everyone's favorite ice cream flavor. Will then say, okay, well, the neighbor's strawberry, so your favorite flavor must be strawberry, right? Doesn't make a lot of sense. So therefore, your complexity goes up because your model doesn't really have a lot of information to go off of. Conversely, if you say 10 neighbors, then let's say 7 of your neighbors, their favorite flavor of ice cream is vanilla, right? And only 2 of them are strawberry, and 1 of them is chocolate. And well, if there's 7 neighbors, their favorite flavor of ice cream is vanilla, the chances are, that gives me a lot more confidence to say that your favorite flavor of ice cream is vanilla. Okay? So the more neighbors that you introduce to the model, the more information you're giving your model to make a prediction based off of. That's why the complexity goes down. It makes it very easy to make a final prediction. It says, oh, there's so many neighbors that are a member of this class. There's so many of you have this label. So it's easier it's easier to make a more confident prediction as to what this new data point or what your favorite flavor of ice cream is. Okay, so that's complexity versus the number of neighbors in K-nearest neighbors. And lastly, I'll talk about how you can use K-nearest neighbors in both classification and regression. So The example I gave at the beginning was actually using K-nearest neighbors. I'll actually write it out here so you can see what it looks like normally. K-nearest neighbors. Okay. The example I gave earlier is using KNN in a classification context, where I want to determine, are you part of class A or class B? Are you class vanilla or class chocolate or class strawberry? You can also use K-nearest neighbors in the context of regression. So again, I will draw another graph here. Okay. And this time, well, I don't want to make a prediction for a class, but I want to use this extrapolation concept. Again, love that word. Let's say on the bottom axis you had shoe sizes. And on the y-axis you had someone's height. Okay? The lowest shoe size we'll say is a 1. The highest shoe size we'll say is a 20. Okay? And let's draw some data points in. So, generally speaking, people with larger shoe sizes tend to be taller. So we'll make the assumption that as shoe size increases, height will generally increase. But we know that's not always true, so we'll put some data points in the outlier zones. But in general, there is a correlation between shoe size and height. So we now have these data points. This is the data given to us. This is the information that we are conscious of, we are aware of. It's documented, it's visible, it's transparent. This is the information that we know. But we want to use regression to figure out if we introduce a new data point, either perhaps in the future, what is a size 21, what is the height of that person, or really anywhere in our data set, can we predict what that person's height would be? Right? Upside down triangle. Okay? And so the way it works here is that we can still use K-nearest neighbors. Again, let's say K is equal to 3 in this example. We want the 3 nearest neighbors, use the information between them to determine this is what the most likely height would be for someone new introduced to our data set. Okay? So K is equal to 3. We're going to focus on 3 neighbors here. Okay? Let's say that we want to make a prediction for someone whose shoe size, we'll put a little tick mark right here, zoom in some. And let's say this is shoe size of 9. Okay? Make that a little bit clearer for you. Shoe size of 9. So we'll draw a vertical line. I'll do it in a different color this time. Vertical line. Okay? We want to see the 3 nearest neighbors to this line. First one will be this data point, will be this data point, and that's the eraser. And this data point. Those are the 3 nearest neighbors to our input of a shoe size 9. To get the predicted height of someone who is shoe size 9, we will take the average between this data point, and this data point. These 3 that are closest to size 9. The average is likely going to be somewhere around here. Right? With this, the average height of these people with these shoe sizes, where it matches up with this green line right here. Okay, so if I get rid of some of the junk here, our extrapolated or brand new data point is going to be right in here, right? So someone with this shoe size 9 is going to have this height. We'll just say that at this data point, maybe it's 5'6", 5 feet and 6 inches. Okay, that's how K-nearest neighbors works for a regression problem. You take the 3 nearest neighbors for a given input, and the average of those 3 neighbors will determine your corresponding output. Okay, so that's K-nearest neighbors. I hope this information was helpful to you. If not, please feel very welcome to leave as much feedback as you want in the comments. And if enough requests, enough demand is out there, I'll even remake this video. But if you learned something, I hope you can use this to go forward in your machine learning pursuits. And I wish you the best of luck as you continue to do so. See you around.